the titanium are metals that are very hard to extract. Not just the extraction, they are something that are being mined actually. So the act of mining is something that goes against with the global agenda, which is sustainability. So in this work, we want to look for sustainable materials that can have the properties of these two gold grade de- gold grade dental implants that have been used. Thank you. Next slide. So in this work, we are going to be using the finite elemental analysis. Final elemental analysis is a computerized method used to predict how products or structure will react to real-world forces like heat, vibration, stress, and fluid flow. It is worked or programmed based on the principle of second Newton's law of motion. So this finite elemental analysis simply refers to a process to simulate physical phenomenon uses using mathematical models. So now instead of going to the lab or taking somebody to carry out a real-time experiment, like in the case of dental implants, it is a very difficult phenomenon to just construct a dental implant and then have to impute it into a real person or a subject to take a lot of time to understand the compatibility of this product. So in this case, simulation is a very, very important or alternative way of doing it, in the sense that you use a computer within short period of time, you'll be able to obtain results that will match years and years of experiment. So the quest for the optimal dental material. The gold standard dental material is known as titanium, and the titanium is made up of a composition of titanium alloy as the primary host material, with 6% of aluminium and 4% of vanadium. So normally titanium is a metal, but with incorporation of aluminium and vanadium, it becomes what is known as grade 5 titanium, used as the gold standard for dental implants. So one of the advantages, or should I say, okay, the other material we are going to be dealing with in our comparative study is the zirconia. Zirconia is a product gotten from a metallic mineral called zirconium. When zirconia is extracted and exposed to oxygen, it becomes zirconia, which is now a ceramic. So now this ceramic is also incorporated or doped with deuteria to be given a result called TZP. And now this TZP stands for tetragonal zirconia polycrystal. It also provides a very, very good ceramic with enhanced property for dental implants. So in the case of our study, or for my own research work, which I'm presenting part of it as this conference, I am trying to use zinc, calcium, aluminium silicate glass as an alternative for zirconium and titanium. So this zinc, calcium, aluminium silicate glass we are proposing is unique in the sense that it can be obtained purely from waste raw materials. So it is 100% sustainable. If we take zinc, for instance, we can use raw materials or waste materials of used batteries, or even use roof zinc to extract zinc oxides from. Then we can extract calcium oxide either from waste bones or waste eggshells. Aluminium oxide can be extracted from used aluminium cans, and silica oxide can be extracted from broken glasses. So this very combination of zinc, calcium, aluminium, silicate components is a very, very good and sustainable materials. We are trying to see if it can also be used for bio for dental implant in the case of bio in the case of biocomponents. So thank you. Next, the zinc oxide actually in the composition provides. Yeah, we can go back to the previous slide, please. The zinc oxide actually provides what is not known as antibacterial action based on previous literatures. Calcium oxide will promote bone integration because we all know bones are almost 90% made of calcium. Aluminium oxide will enhance the mechanical strength of the composition in general, whereas the silica oxide will be the host or the glass forming oxide. Thank you. We can move to the next slide. Okay. The study objectives or approach will be to quantify the stress distribution and deformation within zinc, calcium, aluminum silicate glass dental implant under simulated maximum chewing load. So what we are going to be doing here is we are going to simulate a chewing potential or chewing activity going on for a certain number of days to see how this very different material will react, and then we'll be able to make conclusion if our zinc calcium aluminum silicate glass can be used for this very activity. Then we are going to discuss about the compatibility, the comparison between zirconium and titanium. Then we are going to identify, based on our simulated results, we are going to see and identify possible failure risks and critical stress zone for each material using finite elemental analysis. I've discussed what finite elemental analysis is. Okay, this approach is a computational approach or model. Is a computational model that will simulate 800 Newton of chewing force. Why we are using 800 Newton of chewing force is the average chewing force for an average individual is around 70 to 150 Newton, and the maximum for different activities like chewing of bone is around 500 Newton to 700 Newton. So we have even taken it a bit further to 800 Newton to avoid any unnecessary risk. Thank you. Next slide. So the materials and methods. So in this simulation, in this work, what we'll do is to first of all create the dental implants. So to create the dental implant, we make use of a software called SolidWorks with the help of someone from metallurgical and material engineering from ABU. We design these two different dental implants. We can see different designs here from COMSOL, from SolidWorks, and then we imputed them or uploaded them into COMSOL multiphysics for our analysis. So we can see that the dimension is taken from the actual dimension of a dental implant, which is 4.3 diameter and 4.3 millimeter in diameter and 10 millimeter in length. So you can see the first one is a more simplified version and the second one is a little bit complex. So we decide to go with the first one to avoid, because using the second one, if we can see thread above and we can see thread below, and each thread consists of hundreds of faces. So to simulate thread with more faces, sometimes the simulation might not even work, or it will require a very high computer with very big RAMs. So we decide to go with the second version for simplicity, not for any superiority of design or anything. For simplicity of simulation, we choose the first design for this work. Move to the next slide. So in COMSOL, initially, the first thing you do is to first of all create your geometry, design your material. But in our case, we are not designing the material in COMSOL. So what we do is to import the material from SolidWorks, which is of course doable. So after importing the material from SolidWorks, you already have your material with certain geometries. Next thing is to insert material property to your material that you have already inputted. So in this case, we need 3 different material, but again, to do a parametric study is very difficult. We decide to use the simpler version of it to carry out to use first material, let's say the titanium. When we allocate material of titanium, we simulate first and we keep the data. We now allocate material for zirconium and simulate. We now allocate that of zinc, calcium, aluminum silicate and simulate. Then we make our comparison. So what is required of us for this mechanical simulation in COMSOL? Actually, you do a lot of simulation, which include thermal simulation, optical simulation, and so on. But for this, we only need mechanical simulation. So we just went for the mechanical testing. And what is required of us in the material assignments will include the Young modulus of the materials, where if we see here, titanium has the Young modulus of 110 and Poisson ratio of 0.35. So we assign these material properties to the three materials in a separate simulation, or sometimes you can do the simulation at the same time. When after getting the result, you now change the material property and simulate again, so that you have your three different comparative study. Let's move on. Okay, this is the COMSOL. So I did not put the flow chart of the COMSOL, but I have already started saying it. In the COMSOL, when you open the material wizard, it will display its interface. And one beauty of COMSOL is whatever you are seeing is a visual, is something that is visual. The moment you are doing your material assignment, you'll be able to be seeing the changes. So here, after importing the design, we now assign materials to it. Assigning material means some materials are there in COMSOL. So you just go to the library and add them. Like in the case of titanium, we already have a titanium material in COMSOL. So we only go and add, we only added the material there. But in the case of zirconia and zinc oxide, we need to create a new material. So we have to go to certain existing literatures to look for those Poisson ratio and Young modulus of that specific material we want to use, and then we assign it. So after assigning the material for each simulation separately, we need to attach what is called the boundary condition. In this case, the boundary condition is trying to tell the software how, where, okay, we are dealing with chewing code here, and we realize that chewing code, we need to be pressing from the top of the design to the bottom. So we assign fixed constraint in the bottom, and then we assign our chewing code, which is 800, from the top of it. So we know that the force is coming from the top. So in this case, the 800 Newton is assigned to the top of this very design that we have. So in the construction from SolidWorks, we have assigned a lot of boundaries. But for simplicity, we only, in the COMSOL multivisis, we merge all the boundaries and leave the top boundary and the bottom boundary, because that is the only thing we need. So in the boundary condition there at the top, we assign a force, an oblique force of at 45 degrees to press this very design at 800 Newton, which I've already explained that 800 Newton is 100 Newton above the maximum chewing code for a human. Again, that's the loading condition. After assigning all the boundaries, you will now do what is called meshing. We now move to, in the interface, we are going to see meshing, and the meshing normally starts from a coarse meshing to extreme fine meshing. Doing the coarse meshing actually means to take individual parts of this very design, so that the simulation or the COMSOL, the software itself, will be able to calculate at every point of the design. So if you do an extreme meshing, depending on the computer you are using, you might find the simulation to take longer, or not even to.
Hello, Mr. Kamal.
Or the computer. Yes,
You
sir.
have 5 minutes more, sir. You have 5 minutes more.
Okay.
Yes.
Let me move to the next slide. Next slide, please. Next slide. Can you hear me? Okay. So this is what the result we. Okay. I've not the titanium back once. So this is the result that we were able to simulate for the titanium. If we can see that after assigning the property, so this color we decided to choose the color ourselves. We can see the stress distribution here. Red is the maximum. It means there's a problem there, a crack or a bending. So we can see that in the titanium, a little bit of blue is showing at the neck downward. It means that titanium, we know that it's a metal, so it's very strong. It is not subjected to any cracking or bending after the simulation. And we can also see the one-dimensional line, which shows a periodic spike in stress at thread roots. The highest demand is 4.5 millimeter, the apex. So it does not really show any form of bending or cracking. So the clinical insight for this is the stress concentration at the neck. So we can see that the neck is showing a little bit blue, and in our grid line at the site, blue is a little bit ahead. So those parts showing blue yet do not really signify any immediate damage to the construction, to the design using titanium. So we can move to the next slide. We can move to the next slide. Okay, sorry, I did not zirconium, please. The previous slide. Okay, likewise zirconium, we can see a little bit of blue because zirconium was embedded with in fact it is a dental material that have been used for a long time. So I know that consideration has been taken for this. It is a ceramic, and the oblique force we use is 45 degrees. We didn't use 90 degrees because 90 degrees would not really provide any demand to the construction. At 45 degrees, that is when we'll be able to see challenges coming, and we're able to see at the neck, it has a little bit a brighter blue here, showing that the titanium is stronger than zirconium in terms of mechanical testing, but yet it is not close to the yellow and the red, which shows critical condition. You can see that the one-dimensional graph also shows that the stress peak at the thread are noticeably sharper than the titanium. This not a critical stress riser for a brittle material. So it is showing that it is a brittle material, meaning if it is exposed to a little bit bending, it can crack or it can shatter. But for the 800 Newton force, it does not really show that. So it is still good. So it shows that the two already known materials used for this dental implants, according to the simulation, shows a very good quality. Now let's move to the next slide. So this is our zinc, calcium, aluminium silicate glass. After the simulation, using the same method and the same force, we can see at the top that it has reached the maximum and critical point of showing red color, which shows either cracking, bending, or deformity there at the top. So the one line graph exhibits the sharpest, most defined stress peak at each thread root approach. The material, okay, then the displacement. So in a nutshell, what this graph is saying, at the very top, we can see that it is not spread to the end. Immediately at the top, shows it shows the evidence of cracking. So at this point, we can conclude via seeing these simulation images that zinc, calcium aminosilicate glass is not on par with the two glasses. And we can move to the next slide. So the comparative study in this table summarizes that at peak stress location of these three different materials, for titanium, shows it is at the neck, almost similar to zirconia, but for zinc, calcium, aluminosilicate glass, it shows critical zone from the top of it. I think there's a little error there in the result. I'm not seeing the slide. Okay, thank you. The stress profile of one dimension also shows that zinc, calcium, aluminosilicate glass shows peak at the very top of it. It means if we
Mr.
go a little
Kamal,
bit
please
above,
round up.
okay, if we go a little bit
Please round up.
above it,
Thank you.
yeah, if we go a little bit above 800, it might shatter. Next slide. Next slide. So in conclusion, I would like to just frame the conclusion myself. It shows that the composition that we've choose based on the literature we have for zinc calcium aluminosilicate glass, at the very composition that we choose, we have from Umar et al. 2009 is what we have taken, with 42% silica, 18% aluminium, 30% calcium, and 10% zinc is not suitable for dental implant. Whereas we can temper with this very composition by increasing the aluminium percentage. Maybe increasing, not even maybe increasing the aluminium percentage will actually increase the mechanical properties of this glass. So maybe during my work, I will now use this as a benchmark to improve the level of aluminium in the composition, and then redo the simulation again, and hope that this very zinc calcium aluminosilicate glass will be able to compete it's in the market with the two gold standards material that have been used for dental implants. And then we will encourage future work to maybe look at the material, the construction design, since for all the three it shows a little bit more at the neck of the design. Maybe the design might be optimized for future work. In future work, the design might be optimized to avoid any unnecessary circumstances at the neck of the implant. Thank you for listening.
So, Mr. Kamal, please, we want you to open your video. Hello, can you hear me, sir? Hello, Mr. Kamal. Thank you so much. Hello, sir. Please, can you open your video?
I can hear you now.
Okay. Can I go on? Can you hear me?
Yes, I can hear you.
All right. So, what we're presenting, we presented the calcium and aluminum silicates as a novel material. And
Yes.
one of the things I was looking forward to seeing was to see maybe at the end of the day how this novel material was kind of better compared to the other and
Yes.
the other one putting later. So, but looking from your motion and what you have just shown us, it appeared to be
Yes.
that maybe that's not the case, and that brought about the question of so um, like what have you really achieved in this work? Thank you.
Okay, it's a process actually. Thank you for the question, but the inclusion of zinc within the matrix of the glass is what we think will bring more to. Because if you take titanium, for instance, on a long time, titanium is a metal, and it has this corrosive property, and then because of because of how stiff titanium is, and then it is more stiffer to human bone. This means that the metal takes the weight of any chewing that is coming when you have a titanium implant. So there's what you call stress shielding. The bone that surrounds or that is closer to that titanium become weaker, and then later it degrades. Then there's the issue of color when we are using titanium. Titanium is gray in color, so some people, if they are constructing even the tooth itself or any implant that might show, some people don't like the color. So the combination of zinc, calcium, aluminum silicate glass gives this gray color that is a little bit closer to tooth itself. So that is why seeing the color after the fabrication of the glass, and then seeing the bio the antibacterial property of zinc oxide, we decide to go into simulating. But at the one of the limitation of this very work itself, or the is using one simple composition for the simulation. So I stated it at the end of of the presentation that increasing aluminum, we only have 18% of aluminum in this matrix. So increasing aluminum to maybe 30% will improve the mechanical property of this very zinc aluminum silicate glass. And we hope with the integration of improved aluminum, we are going to have not just antibacterial property by including zinc oxide, we are going to have a very strong mechanical property. But at this stage of the work, we know that inclusion of zinc oxide improve the antibacterial property, unlike the other ones they don't have. And we can see that yes, the top has shown a little bit that at the top we see that it is in a critical condition, that there might be crack, but yet it's not the whole stuff that have crumbled. So by little improve in the glass composition or in the glass ceramic composition, we might be able to overcome that. At least it's a step to see that yes, it is possible. Thank
Thank you, sir, Dr. Kamal.
you. Yes, ma'am.
I wanted to know,
Yes.
these materials, have they been used before now? Where do you
Yes.
come in research gap? And you didn't show us literatures, citation, and do you reference anyone for us to flow and know, okay, this is what is on ground, this is what I'm bringing in. So what actually is the research gap we are now filling? And for future purpose, there should be literatures to show us existing works so that we can understand your unique contribution. Then also want to ask that these materials are very ethical since we are dealing with human. So for the improvements they are bringing to the durability of the materials used for dental implantation, are they already accepted ethically? Thank you.
Okay, thank you very much for the question. The titanium and the zirconium are well established materials that have already been used for years in the dental world. But the zirconium the zinc calcium aluminum silicate glass is something we are working on. For the citation issue, they are actually in my work, but it's an oversight, which thank you for correcting me. I should have added a lot of citation in it, but it's an oversight from my side, from my part. But titanium and zirconium are materials that have already been used for years in the case of dental implants. For zinc aluminum silicate glass, the gap there and we are seeing is the case of sustainability. If we can bring any material that is sustainable, any material that can be obtained, I've explained that zinc calcium aluminum silicate glass is a unique glass because it is a glass that have 100% composition obtained from waste material. So we have tested other things like radiation shielding properties, like optical properties, thermal properties of this glass. Now we are just going into seeing if it has bioactive properties too. So by doing this simulation and more simulation like the ion release and so on, we hope that we'll be able to have a composition that can compete with titanium and zinc and zirconia, which are now market grade, and the composition or the material that are used globally. Thank
Well, thank you very much for that presentation. I appreciate the fact that you also partnered with the methodologists that are helping your design. Um, I don't know if you can go to the slide that you have limitations. Yes. Okay, yes. So you presented the previous two as to how certain limitation presented their limitation, but your own material you are choosing based on your study, there was really no limitation. Are you trying to say that the material is a perfect material, there's no limitation with it? I just want you to give a clarification on that. And if you go to your clinical benefits of that same material, you listed antibacterial action, you listed promoter, it promotes, no, that same slide, sorry. Yes. So you said it promotes bone integration. So I just needed some clarification because it's a health matter. When you mean antibacterial action, does it mean that certain components of that zinc, calcium, material that is in, does it certain component decomposes or does it disintegrate to start performing that action? Are you saying that certain components of it, if it's a glass ceramic, as you stated in your topic, this doesn't mean that certain components of those or that material decompose to start performing those actions that you listed? I just needed some verification. Thank you.
Okay. Thank you very much. So why I did not input limitation is a new something we are proposing. So it has not been used to even come up with its limitation. If we have, let's say, fabricated it and then constructed and then put it on someone to use, we'll have known its limitations too. I know definitely it is going to have. But for now, what I'm just trying to say here is that zinc oxide, when inculcated into most of glass matrix or any other implant matrix, it has these antibacterial properties. It means it's not easy for bacteria to come and attack that very part. And it has been proven based on literatures. So then what the meaning of why we say it can also integrate into is because of the viability of calcium oxide. It's like you are taking another bone to attach it to another bone. So they act in the same way. So there's a tendency, if we are using it not just for dental screw, let's say we are using it for bone fillers, it will integrate into your bone system as though it is the bone itself. Because of the existence of zinc oxide, it will not be prone to bacterial attack. So that is what it means, the antibacterial property here. So it will not be prone to bacterial attack because of the existence of zinc within the matrix. Because of the existence of calcium, it will integrate into your bone as though it is the bone itself. So that is what we mean by that.
Yeah, thank you so much for your presentation. I think the last question. You were talking about the model that you use for your simulation, but you didn't show it.
No, we did not use a specific model. We use a software, and in the software, all we needed to do is to simulate a chewing activity. Like within the setups, when you have COMSOL multiphysics, okay, you subject the the design to a chewing force. In our case, it's just a force that is subjected in a 45 degrees angle. So in the study, in the end, you'll be able to give command to arrange. Maybe what we give to this simulation is for it to have to chew or to subject the design to a chewing force of 10 times per day for 100 days. So that is what we're able to see. That is when we're able to see those cracks. So we just subjected it to a force hitting, coming back and forth in 45 degrees to the design 10 times per day for 100 days. So it's not actually a model itself, but it is something that is imbued in the software that any other person can do. The only specialty or the novelty of this one is we are using a material that has not been used before, but we are not actually using a specific model or anything specific that is new.
Okay, thank you so much. I think I want to believe that there's a model running that software. So the software is not just a software, but we have a model. And maybe if you care to look at the documentation of that that software, you see there's a model. Because there can be simulation. And if you changing those parameter values at 45 degrees, it goes into a model actually. I understand and I appreciate the fact that you used that the software, it's okay. Or I think we as I was just looking at the audience that you're also speaking to. There will be also audience that comprises of mathematicians who also would have loved to see that the model that runs the software. Nevertheless, it's a good one and well done.
Noted.
So
Noted.
last
Noted, sir.
question. Okay, last question, and then we'll end that session. Thank you, sir, for the work
Thank you, sir.
from your late partner of the ceramic. For sure, one that zinc is a metal is has this natural antibiotic effect, and like your calcium also. For sure, calcium and magnesium they have this. It promotes the bone and but my issue is the issue of millennium. I'm asking the question similar to what one of our person asked earlier. You know that for sure, aluminum is a bit carcinogenic. That's why nowadays people are trying to do away with these aluminum pots. When you are talking of increasing the concentration of aluminum in that compound, I hope you are taking notes of the effect of aluminum. And you know, like, this material will be used as tools and the dental and this compound will need actually I know that glass material in terms of reaction they then want to react easily, indicating proper, but eventually there's any reaction with some things you drink or you eat, and this aluminum get to human blood. I hope you are taking notes of the effect of that, and I wish you work with maybe the microbiologist to be able to check this for you. Well, we want to respond to that.
Okay, sir. If I've gotten the submission is that how do we deal with the existence of aluminium in the composition? Because we believe aluminium has certain disadvantages in human body. If I'm right, because the network was not okay. But was it what he was trying to illustrate?
It's talking about the aluminum part of it, that the carcinogenic effect of aluminum has been known these days. That when you now are considering the use of aluminum, that's and increasing that concentration as well. That have you considered that part? And do you maybe it's not suggesting we need to work with microbiologists to look into how that will work properly so that it will not cause something else or another health issue.
I
Did
don't
you
think
get
this is something. I don't think this is something for me to respond, but I will note it down and then make more research on it. Thank you for the.
okay?
Uh-huh.
All right. Thank you so much, everyone. We want to appreciate you for staying to and now there's the good news. The good news is that
Thank you
what's
very
the